Okay, so we'll start in a couple of minutes, a minute or two. I can see that lots of people are joining now. And I have remembered to record again this week. Today we have got Miss Wanstall, who is in the background. You can't see her, but she could put her video on later maybe and say hello. She's going to be looking at the questions, and if it's appropriate, she'll sort of butt in, but if not, we'll do what we did last week or yesterday in fact as well, and I'll wait till the end and answer any questions at the end. So if you have a question, please write it in. It will be answered by during this webinar, and then I'll post the whole webinar on the classrooms. Just to remind you, there will be some exam questions following this, a Google quiz version like you had last week, or a Google Forms version as well. So those will be in your classrooms. Okay, so the participant numbers have stopped going up, so I'll get started. Okay, so you should be able to see the slides that you've got in front of me, and you should recognize this image from last week. This is a transverse wave, and we've got the little arrow here, this little bit here, just to remind us that the T for transverse means that this bit here going down, the oscillation or vibration. Don't say movement, please, because you don't always get the mark for that. The proper term is oscillation or vibration, is perpendicular to the direction of the wave, and that is unique for transverse waves. Good. So the electromagnetic spectrum, it can be depicted on one single wave. You'll often see it like that, but it is actually, and each section is divided according to wavelength and also frequency, but most commonly wavelength, into different sections. You will need to know the order of the waves in the electromagnetic spectrum. There is a song of which I am not going to play, but I'll let you treat yourselves to that later. It looks like this. Okay, you just type in the electromagnetic spectrum song. As long as you get this up, it is quite catchy, but also quite bad. So that you can look at to recall the order. We can see then that the radio waves have the longest wavelength. Remember, it's from any two points. So here we've got from peak to peak, or it could be from trough to trough, or even midsection to midsection across there. So you've got the radio waves right down to gamma rays, which are the very high frequency waves there. In the middle, we've got the visible light. We'll be talking about this in a bit more detail, but we can see that spectrum of colour from red all the way through to violet. The colour of the order of the colour that Richard of York gave Battle in Vain, which denotes the different colours of them, Richard being red, of orange, York yellow, so on and so forth, which I'm sure you're all absolutely familiar with. So what we need to know for higher tier then is the use and why they're useful. Essentially, what is it about their properties that make them useful for what we're using them for? So we've got radio waves, which are for TV and also radio, as you might have guessed. So these are long waves, and they can travel quite far distances. Okay, so they're useful for that. We've got microwaves. Most of you will be familiar with a microwave oven for cooking your food. Interestingly, in a microwave, I haven't got a picture of it here, but what the microwaves do is they agitate, which means vibrate the water molecules within your food. Those bonds between the O and the two H's, microwaves cause those to vibrate, and so that then by those vibrating, obviously the net result of that is that they heat up, they're absorbing them, causing that increase in internal temperature. So when you're cooking food in a microwave, often if it's like vegetables, you have to put maybe 2 or 3 tablespoons of water in there, because you're heating the water that then eventually cooks the food as well. Satellite communications, including mobile phones as well. Okay, so those are your microwaves that are used for that. The next section coming down are infrared. So we can see here, this is a picture of an infrared or thermal imaging camera. It's not mentioned on here, but they can be used for treating, they can be used for imaging tumours and things like that as well. So if there's a different temperature within the body, the infrared radiation will pick that up. They are less dangerous than some of the other higher frequency waves. We'll talk about that in a minute, but they so that's why they're often used. All we need to know for our GCSE is that they're used in thermal imaging cameras, electrical heaters, and can be used for cooking food as well. So after your infrared, we have got visible light. So just think about this for a minute. Infrared comes in at the red part of visible light spectrum, and after visible light we've got ultraviolet, which comes out at the violet end. So another way to remember them is you have infrared before visible light, then you have the red wavelength, and then after visible light or the violet wavelength you have ultraviolet. Now visible light is used in fibre optics, and so what we do with that, excuse me one moment, thank you. Apologies for that. I have a 5-year-old. So where was I? We have here then the visible light, so fibre optics. It's this picture here. Now we can see from the work that we did on light rays last week that we've got an infrared, a light ray coming through here, and we could do a normal dotted down at this point here. And what happens then, and the reason why fibre optics are so quick is because the information is travelling at the speed of light down this fibre optic cable, and we can see this total internal reflection happening here. So visible light is used in fibre optic communications. It's also used for if you've ever had like a camera inserted into your stomach, then you can they use fibre optics for that, and then they can get images of whatever might be going wrong with the stomach or something from there. UV light, most of us will probably recognise it as being for sun tanning, those sunbeds, which as we're all aware are highly dangerous, but also energy efficient lamps as well. And then the last two have been banded together, X-rays and gamma rays, and those are for medical imaging. So we know X-rays, you have an X-ray of a broken bone or maybe dental of your teeth, but also gamma rays can be used for imaging as well. They provide a really high resolution image. So you know, if it warrants it, then a gamma ray can be used for medical imaging. Naturally, you can't have too many of those. And also for treatments as well. So the treatment, let's just think about this over here. What the gamma ray does is it kills the cancer cells, okay, by essentially stopping them from replicating around there, so the tumour can be reduced in size from that way. There's different ways of doing it. Again, this is not in the GCSE, but it is interesting for you to know that radiotherapy, which is sort of X-rays coming down, and also some gamma rays as well, will hit the tumour, but also around the tumour as well can damage other healthy cells. So it is a bit of a blunt instrument in that respect. Proton beam therapy is just as effective, but also it doesn't damage as many healthy cells, so you're getting just to the point of the tumour. So for example, if you have cancer in the brain, a brain tumour, then that would be far more beneficial to an individual to have proton beam therapy rather than radiotherapy, and the chances of survival are much higher for a person who has had proton beam therapy than radiotherapy. Okay, so those are the uses that you need to know about. We'll come back to these higher ones, the higher frequency waves, in a bit, but I want to first next talk about how radio waves are used. This is higher tier only, and the questions are normally worth between 2 and 4 marks on them, and I have actually put a question in for you to answer on this as well. It looks like a complex diagram. This is A level that you've got in front of you, this diagram, but I've pulled out the 2 most important things. At the transmitter, so where the radio wave is produced, if you have oscillations of the same frequency in an electrical circuit, they can be emitted across a space, across a gap, also across a vacuum, which we wouldn't need because we're down on Earth, but that can happen. And then the receiver then will absorb those radio waves, and it will create an alternating current of the same frequency in the receiver at the same time. Okay, so that is how radio waves can be transmitted and received. Okay, and the key words there are absorbing the radio waves. It sets up an AC, or alternating current, of the same frequency. Okay, so that's how you would answer any question, excuse me, that would be about that. Now, let's look a little bit more about the higher frequency. So the key idea is, why are high frequency waves more dangerous than low frequency waves? And we can think about our wave speed equation to understand this. So we know that all these waves travel at the same speed. They all travel at the same speed. But the high frequency waves have a very short wavelength. And so if you think of one wave as transferring almost like one packet of energy, in that speed, for that speed to be exactly the same all the way down, they're transferring so much more energy. You're being absolutely bombarded with energy. Whereas with a radio wave, where the wavelength is much longer, the energy that is transferred, that packet of energy, almost as if you will, that is transferred in that long wave, it's spread out over over a bit more of a distance. So high frequency waves are much more dangerous because they transfer more energy. And so much so that they're ionizing. Now this links back into work that we did on P1. Some of you won't be able to remember this, some of you will. At this point it doesn't matter because we are at the end of year 10, not at the end of year 11. But just to remind you, P1, we looked at radioactive decay and half-life, and the becquerel is the unit of activities, the unit of decay per second of a radioactive substance. The half-life, if you'll remember, is the time it takes for it to lose half its radioactivity, and then it halves, and then halves again, and halves again. So we've got this radioactive decay going on. This you might recognise actually from photosynthesis and the inverse square law. We don't need to know this. This is A level in terms of ionizing radiation, but it's a good, for those of you who are considering A level physics or A level maths indeed, the inverse square law will be useful to you, and you do need to apply it in your biology when we do photosynthesis. But we have how the strength of the ionizing radiation decreases the further away that you are from the source. Now, this is important because of people like radiographers and also people who take x-rays as well. They will need to be, if they're doing that day to day, day in, day out, they will always, and you will have seen if you've had this done, they will always be behind a screen. They will always move to the far side of the room or something like that, because the ionizing radiation is lower from here. Now, to detect, we use the sievert. And this is a measure of the risk of harm to the body from the radiation. Okay, just so you recognize that word sievert, and that is what that does. So ionizing radiation, and by that I mean, well, actually from ultraviolet, because we'll think about that, from ultraviolet, X-ray, gamma ray, these are all ionizing. And so we use that property of the ionizing radiation in X-rays and gamma rays to kill cancer cells. We talked about that here, didn't we? We said that the ionizing radiation is great because it can kill a cancer cell. But if it can kill a cancer cell, it can kill a human cell as well. And so what it does is it actually damages the DNA. If we think back to our biology, that will cause a mutation in the DNA. So if it replicates again with that same mutation, then you've got the possibility for cancers and tumours to start growing. So ultraviolet exposure to UV rays in sunlight causes skin cancer because it damages the DNA of the skin. Okay, and so repeated exposure without any suntan protection would cause, or could cause, should I say, skin cancers to develop. X-rays with their increased frequency are even more dangerous in that sense, and the gamma rays on top of that as well. Okay, so that is the information about that. I'll see how many questions we've got coming up. No questions so far. That's good. Have a think about those questions that you've got from there. I'll go back and do a little quick summary review of all of these. We've got a little poll as well. Yes, hello.
I had two questions. What does the colour spectrum mean?
What does what, sorry, mean?
The colour spectrum.
The colour spectrum. Oh, this is essentially what we're talking about when we talk about colour spectrum. We're talking about this bit here of visible light. So I don't want to use the word rainbow. We could use the word spectrum instead. You'll recognise it as a rainbow. When white light is split in the rain, that splits the sun and the rain, it splits white light into and what we observe as a rainbow. But in science, we call it a spectrum of colours, and they're always seen in this order because they have different, each colour has a different wavelength. Now for triple science, we'll go on and look at that in more detail about how we see colour and link that back again to some biology of the eye and things like that, which we'll be doing on the triple only webinar that I do on a Tuesday. Okay, well, was there another question, Miss?
There was one more which I answered, but I'll bounce it to you in case I gave a twitchy answer. Why is radiotherapy still used if a proton beam is better?
It's newer, less people have it. Okay, and it's becoming increasingly used. Over the past maybe year or 2 years, it has been found that this type of therapy is becoming used more often. But like with everything else, in some cases, it wouldn't make a difference between proton and radiotherapy, depending on the nature of the tumour. But the proton beam would definitely be used on something which is needs to be absolutely pinpointed exactly. Miss, I don't know if you remember the boy that was taken out of a hospital in Southampton because his parents wanted him to have proton beam therapy. The hospital said, we're not, were dragging their heels, so to speak, and they took him abroad, can't remember where, to have this treatment done, and he survived. And I think actually it was in the news a lot at the time, and since then I think that they have been using proton beam therapy a lot more widely than they had. These machines, as we can imagine, are highly specialised. It would only be some cancer centres that have them. Anything else, Miss, from
I've got, will we cover this topic in more depth when we return to school?
We will, in the sense that we'll have revision sessions on them and things like that. Absolutely. What you're obviously not doing is having a go at practicing them. What you can do now is, when you answer the questions on these afterwards, your teachers will be able to identify the gaps that you've got as well, and so then we'll be able to sort of give feedback from that. But everything that is being covered in home learning will be covered again. We've got a whole year where we don't have to teach you anything new, so well, not quite a year, because obviously it's till May, but we will go over everything from year 9 and from year 10 as well.
And could you explain proton beam again?
The proton beam, essentially, as I say, this bit is not where you're going to be. This is for your understanding, your knowledge, okay? But the proton beam is essentially, you've got this beam of protons, which are, if you think about it, a single proton of an atom, okay, can ionize if it is pushed fast enough, can knock, by ionized we mean knock the electron, okay, off the atom, damage the DNA of a cancer cell. And because it is such a narrow and small particle, it would not be damaging. You can be very, very accurate with where you place it within the tumour. So it would ionize the cells of the tumour and then damage those their DNA. They all work in the same way, okay? It's just about whether you're using one that is more precise than the other.
We've had a request to go over slide 30 again, Miss.
Slide 30, this one, yeah, absolutely. So this is the radio wave slide, okay? So here we have, this links back into your understanding of electricity, okay, and alternating currents and direct currents. So we know that an alternating current is one that flips backwards and forwards, backwards and forwards, backwards and forwards, okay, whereas a direct current just goes in one direction only. Okay, so an alternating current, of which we have in our homes, we have the the frequency in our homes, the alternating current in our homes, can alternate and oscillate at the same frequency as radio waves. Now, if that then gets transmitted through a transmitter, that's the only thing you need to know. You can send them, as we know with transverse waves, they can move through the air. Okay, they move through the air like this. If that then is picked up by a receiver, it can cause the electrons within the receiver to form to flow, but what's important is that they're flowing with an alternating current of the same frequency. Okay, so it just essentially the alternating current that is on the transmitter going up and down here, that then is pushed out into a space that you want to move it into. If a receiver is then, you've dialed your receiver and you're picking up, you can change your signal to match that frequency that's coming in, then that alternating current can be picked up by that receiver, okay, and that then can oscillate those electrons of the same frequency, and then you can then pick up and sort of decode, if you like, whatever it has that has been transmitted. So you probably won't have them because you'll have digital radio in your car now, where it's all push of a button. When I was young, and probably Miss Wansell was young as well, you would turn a dial and then you would pick up your radio stations like that, and all that you're doing then is trying to get your electrical current on the same, so it can pick up the same frequency of radio waves that are being picked up as you're driving around in your car. That is how that works. You do not need to know the exact how, okay, how does a transmitter work? How exactly does a receiver work? It's the principle of it that you need to understand.
Linked with that, they've asked if slide 30 is in an exam, what context would it be in, and what would be likely to be asked?
Okay, so there is a question on the Google form, on the Google quiz that you've got, that will be talking about that. But it would simply be how can radio, you know, how do radio waves, how are radio waves detected at a receiver? Something like that, and then you would quote this little bit here. It would absorb it, and an alternating current of the same frequency could be established. So therefore, you know, they've received those radio waves. All right. So very deliberate language. Alternating current, same frequency as the radio wave is sufficient for any question that would come up on that. And as I say, it's a small part, between 2 and 4 marks. It was in 1 year, but I don't think it was in on another year of the new exam from that. Yeah.
That's all the questions. Someone asked about uses of radio waves.
Uses, TV, okay, not your satellite TV, not Sky or anything like that, but your old school TV, and obviously radio. Those are the two uses of radio waves that are from now that we need in the spec. All of these bits here, this is just copied directly from the information that we have to give you, and I've added sort of some interest bits around it about the proton and the radiotherapy and things like that. But what happens is with the ultraviolet and all of these, the key word that we're using here is that they are absorbed. We've talked about whether they've been reflected back, and triple students, we looked at ultrasound yesterday where we're talking about reflections. Here, these are being absorbed, and just make sure you're clear about that, okay, because they're being absorbed and doing damage. Essentially, if you have too many X-rays, well, you can't have an X-ray if you're pregnant, because there's damage to the fetus, isn't there? There's a possibility of damage to that fetus, so you wouldn't be able to have one. And so the X-ray itself is an image of the absorption of the X-ray into the bones themselves. So yeah, too many X-rays are, you know, and by too many I mean lots and lots of X-rays are not good for you either. Oh, any more questions, Miss? Are we all good?
No, the only one I'm going to chuck out there, Miss, for you is speed cameras and
yeah.
waves they use.
Yeah, go on then. So what would you want to go over on that one, Miss, or?
No, I'm happy for you to. It's just my brain always remembers the speed camera questions coming up.
Okay, so if we're looking at the speed cameras, we're looking at most likely would be well, depends on what you use them for. If you've got the gun, the person, you know, you see them with there, that might be radio waves that they use from there, from that. But you would use, in that one, the question could be more around speed equals distance over time. And they would give you, you know, it took this long to get between X and Y, radio waves, or the frequency of whichever wave that it is that they're using, travels at X speed, so how fast was the car going? Okay, so you're using that equation to work out for speed cameras and things from there.
And we've got, do X-rays affect all different cells?
Yes, they would do if they can. So X-rays are absorbed by bone cells from that, so they won't, they can't sort of pass through them, but they are not nearly as dangerous because they don't carry as much energy as gamma rays. So they would affect all cells, but to a lesser extent than a gamma ray would.
And does this sort of thing apply to ultrasounds?
No, because ultrasounds are the higher frequency sound waves, and they are longitudinal waves. So ultrasounds are used for scanning fetuses, for example, because they are not dangerous in the same way as these electromagnetic waves of high frequency electromagnetic waves. It is a totally separate phenomenon. So don't get confused with ultrasound and make them interchangeable with anything on the electromagnetic spectrum. They are totally separate at that point. Ooh.
No more questions here, Miss.
No,
I don't know.
I have a very small poll, okay, because I accidentally deleted some this morning. Don't know why, just did. So let's see if we can remember the order of the waves in the electromagnetic spectrum. This is a big ask. This is a big ask because you haven't watched the awful song, but let's see as we're going through them what we think.
What's funny there, Miss, is I started singing the song in my head to get the order right.
And actually, when the if that question comes up, there's a couple of things where everybody starts doing the same. Okay, so I think people who are confident to vote have pretty much voted. To go up a little bit. Overwhelmingly, which is really encouraging, I'm going to end the poll there. Overwhelmingly, people got this right. Okay, radio waves, microwave, infrared, visible light, UV, X-ray, gamma. Okay, so that's that one. But again, I really wasn't expecting you to have known that one. A use of microwaves then. Okay, I'm going to end that poll there. Most people got it right at satellite communication. Actually, infrared can be TV remote controls. You know those little pointers with the little red beam that comes out of them? You know, people have them for the whiteboards and all those little things. They're infrared little guns in that sense. And so those ones are for TV remote controls. Medical imaging, if we used a microwave for medical imaging, remember I said that a microwave agitates the water molecule. We are made of quite a lot of water. We would get, you know, we'd essentially boil if we were using microwaves and that. So it is satellite communications. And I believe I didn't delete that one either. Okay, so I'm going to ask this a lot. It's important. You have to know it. What is a wave speed equation? Cool, I'm going to end the poll there. Everybody's pretty much on that. Wave speed equals wavelength times frequency. I've just noticed that there were some questions down here that I forgot to mention a poll on, which is how is gamma radiation emitted? Okay, and I'm just going to tell you this now. It's this little bit of the slide that I missed out on. It was from P1. So when the atom, when unstable atoms break down, they emit three types of radiation: alpha, beta, and gamma. Okay, so the gamma radiation is emitted from the breakdown of unstable atoms, the nuclei of unstable atoms, and you'll have done alpha and beta and gamma, in point of fact, in P1. I think it's the last topic of P1 that you'll have it from there, but it's just one of those crossover pieces of information from that as well. So that's the gamma, and what happens at the receiver of radio waves. The key language that we lead is that the alternating current is oscillating at the same frequency as the radio waves. So that would be, you know, potentially a sort of 2 to 3 mark question on that, using that key language. Excellent. So, Miss, no other questions on there?
Nothing's come through, Miss.
Okay then, guys, so thanks ever so much for joining in. We've got 75 people today, which is brilliant. I will, well, I say I'm not very good at this. I might ask Mr. Lamb to download this, and we will upload this webinar to your Google Classroom, as well as the questions for you to answer. Thanks ever so much for logging in, and I will see you all on Tuesday, Triple Science students, for your webinar then. Okay, you guys can log off now. Thank you.
Don't forget, Miss, you can stop recording now.